Hello friends, welcome to this lecture. I am Amlan. Today I will discuss about fine structure of hydrogen spectral lines. Okay. When the lines of hydrogen spectrum are observed by a high resolving power spectroscope, each line is found to consist of several closely spaced lines. That is, lines differing from one another in frequency by very small amount. This fact is expressed by saying that hydrogen spectral lines have fine structure. For example, the H-alpha line of Balmer series have 5 fine structure components and H-beta lines of Balmer series have 7 5 structure components. Okay. Now, Sommerfeld tried to explain the fine structure of hydrogen-like atomic spectra by considering the relativistic variation of mass of the electron, deducing the expression for energy E equals to minus mu z square e to the power 4 by 32 pi square epsilon 0 square L square h cut square into 1 plus z square alpha square by n square into n by n phi minus 3 by 4. Suppose this is equation 1. Here mu is the reduced mass, n is the principal quantum number and n phi is the azimuthal quantum number of the single atomic electron, and alpha equals to E square by 4 pi epsilon 0 CH cut. Its value is approximately 1 divided by 137. Okay. Alpha is called fine structure constant. Okay. Alpha is called fine structure constant. Now, this theory was partially successful. Later, the quantum mechanical expression for the relativity correction was given by Heisenberg and Jordan, and the relativity correction for energy is delta ER is equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into z square alpha square by n square into n by L plus half minus 3 by 4. Suppose this is equation 2. Here L is the orbital quantum number of the electron. Now, this formula does not take into account the reduced mass correction. The additional correction term taking into account spin orbit coupling is necessary, and the spin orbit coupling term is delta E Ls is equals to m z square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into z square alpha square by n into j plus 1 minus L into L plus 1 minus S into S plus 1 by 2L into L plus half into L plus 1. Suppose this is equation 3. So this is delta Ls. Okay. So the total correction for energy is delta E is equals to delta E R plus delta E Ls. Okay. Now if we add equation 2 and 3, then we get this is equals to minus m z square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into z square alpha square by n square into n by L plus half minus 3 by 4 minus j into j plus 1 minus L into L plus 1 minus S into S plus 1 by 2L into L plus half into L plus 1. Okay. Suppose this is equation so this is the total correction for energy. So the completely corrected expression for energy is E equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into 1 plus z square alpha square by n into 1 by L plus half minus here n by L here n by L. Okay. J into J plus 1 minus L into L plus 1 minus S into S plus 1 by 2L into L plus half into L plus 1 minus 3 by 4n. Okay. Suppose this is equation 4. So this is the completely corrected expression for energy. Now let this term is F. Okay. Let 1 by L plus half minus J into J plus 1 minus L into L plus 1 minus S into S plus 1 by 2 L into L plus half into L plus 1 is equals to F. Okay. Suppose this is equation 5. So, using this, equation 4 can be written as total energy E equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into 1 plus z square alpha square by n into this term is F minus 3 by 4n. Okay. Suppose this is equation 6. So this is the completely corrected expression for energy. Now let us consider two states of the hydrogen-like atom. in which for the two states, for the electron, the principal quantum number n has equal values. The total angular momentum quantum number j has equal values, and the orbital quantum number L has values differing by unity. Okay. So for the first state, the quantum numbers are n, L1 equals to n minus half j and s. Okay, so these are the quantum numbers for the first state, and for the second state the quantum numbers are n, L1, j and s. Okay, and for the second state the quantum numbers are n, L2, j and s. Okay, because here only orbital quantum numbers are different. Okay, here principal quantum number and total angular momentum quantum number are same. Okay, for the two states. Now for the first state, if we calculate the value of f, then we get value of f is f1 is equals to 1 by L1 plus half minus j into j plus 1 minus L1 into L1 plus 1 minus s into s plus 1 by 2 L1 into L1 plus half into L1 plus 1. Okay. Now if we simplify this, then we will get this is equals to 1 by j plus half. Now for the second state, if we calculate the value of f, then we get f2 is equals to 1 by L2 plus half minus j into j plus 1 minus L2 into L2 plus 1 minus s into s plus 1 by 2 L2 into L2 plus half into L2 plus 1. Now if we calculate this, then we will get this is equals to 1 by j plus half. Okay. Hence we get f1 equals to f2. Okay. Hence we can write f1 equals to f2 equals to 1 by j plus half. Suppose this is equation 7. Now equation 6 and 7 shows that in the same two state electrons have equal energy given by E equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into 1 plus z square alpha square by n into 1 by j plus half minus 3 by 4n. This is equals to minus mz square e to the power 4 by 32 pi square epsilon 0 square n square h cut square into 1 plus z square alpha square by n square into n by j plus half minus 3 by 4. Suppose this is equation 8. So this is the total energy for the same two state. Okay. Now we know that H alpha line is emitted when electrons in the hydrogen atom suffers transition from n equals to 3 to n equals to 2 state. Okay. We know that H alpha line of hydrogen atom occurs when electrons in the hydrogen atom suffers transition from n equals to 3 level to n equals to 2 level. Okay. Now, for n equals to 3, the orbital quantum number L has 3 values 0, 1 and 2. Now, for L equals to 0, that is S state, J has only one value, that is half. And L equals to 1, that is P state, J has two values, L minus half and L plus half. Okay. So one value is 3 by 2 and other value is half. Now for L equals to 2, that is D state, J has two values, L plus half and L minus half, that is 5 by 2 and 3 by 2. Okay. Now we write the quantum states for n equals to 3 and n equals to 2. Okay. We draw a table. Suppose this table is for principal quantum number n equals to 3. Okay. So this table is for n equals to 3. Now here we write the value of n, here we write the value of L, and here we write the value of J, and here we write the spectral notation of these quantum states. Okay. And suppose this is the table for the quantum state for n equals to 2 level. Okay. Now here also we write the value of n, here we write the value of L, J, and here we write spectral notation. Now this table is for principal quantum number n equals to 3. Now for n equals to 3, L has 3 values 0, 1 and 2. Now n equals to 3 and L equals to 2. One value of J is 5 by 2 and other value is 3 by 2. And for n equals to 3 and L equals to 1, J has two values. One value is 3 by 2 and other value is half. And for n equals to 3 and L equals to 0, J has only one value, that is half. Now here, if we write the spectral notation of this quantum state, then this can be written as 3 2d 5 by 2. Okay. Because here we write the value of n, principal quantum number, and for n equals to 2, that is d state, and here we write the value of j. Okay, and this is the degeneracy. Similarly, this state, spectral notation of this state will be 3 2d 3 by 2, and this is 3 2p 3 by 2, and spectral notation of this quantum state is 3 2p half, and spectral notation of this quantum state is 3 2s half. Okay. Now for n equals to 2, J has two values 0 and 1. Now for n equals to 2 and n equals to 1, J has two values. One value is 3 by 2 and other value is half. and for n equals to 2 and n equals to 0, j has only one value, that is half. Now similarly we write the spectral notation of these states. Okay, the spectral notation of this quantum state will be 2 p 3 by 2. Similarly, this is 2p half, and this is 2s half. Okay, because here we write the principal quantum number. Here the for n equals to 1, there is p state, and this is the value of j. Okay, similarly we write all the spectral notation of this quantum states. Okay. Now here we note that the energies for the quantum state 3 2d 3 by 2 and 3 2p 3 by 2 are coincident. Okay, the energy levels for 2d 3 by 2 and 2p 3 by 2 are coincident, and the energy levels 2p half and 2s half are coincident. And also for n equals to 2, the energy levels 2p half and 2s half are coincident. Okay, that is has same energy for that two state. Now we draw the spectral lines for the H alpha line of hydrogen spectrum. Okay. Now we draw the spectral line for the H alpha line of hydrogen spectrum. Suppose this is n equals to 2 level and this is n equals to 3 level. Now for n equals to 3, L has 3 values 0, 1 and 2. Suppose this is L equals to 0 level, this is L equals to 1 level, and this is L equals to 2 level. Similarly, for n equals to 2, L has 2 values 0 and 1. Suppose this is L equals to 0 level and this is L equals to 1 level. Now for n equals to 3, L equals to 2 level is divided into 2 sub-levels. One level is 5 by 2 and another is the coincident energy level for 3d 3 by 2 and 3p 3 by 2. Okay, so this is the coincident energy level for 2p 3 by 2 and 2d 3 by 2. Okay, and this is the coincident energy level for 2p half level and 2s half level. Okay, similarly for n equals to 2, L equals to 1 level is divided into 2 sub-levels. Suppose this is j equals to, so this is the value of j, this is j equals to 3 by 2 level, and this is the coincident energy level for 2p half level and 2s half level. Okay, so these are the value of L, these are the value of L, and these are the value of j. Okay. Now the transition from n equals to 3 level to n equals to 2 level gives the H alpha line according to Bohr model. Okay, transition from n equals to 3 level to n equals to 2 level gives the H alpha line according to Bohr model. Now here in this case the selection rule is delta L equals to plus minus 1. That is, the transition which satisfy this selection rule will actually occur. Okay. Now, applying this selection rule, the transition occurs from L equals to 2 level to L equals to 1 level. Now transition from L equals to 1 level to L equals to 0 level gives a spectral line, and the transition from L equals to 0 level to L equals to 1 level also gives rise a spectral line. So three possible transitions will occur. Okay, three allowed transitions will possible here. Now here in this case the selection rule is delta L equals to plus minus 1 and delta J equals to 0 plus minus 1. Okay, that is the transition which satisfies this selection rule will actually occur. Now here transition occurs from J equal to 5 by 2 level to J equal to 3 by 2 level. Now the transition from J equal to 3 by 2 level to J equal to 3 by 2 level gives a spectral line. Transition from J equal to 3 by 2 level to J equal to half level also gives rise a spectral line. Now the transition from J equals to half to J equals to 3 by 2 level gives a spectral line, and the transition from J equals to half level to J equals to half level gives a spectral line. So total 5 allowed transitions are possible here. Okay. Thus we explain the 5 different components of the H alpha line according to Bohr-Sommerfeld model with spin relativity correction. Okay. Thank you for watching this video.